in what might be one of the most revolutionary shifts in aviation in decades. The world just witnessed something extraordinary: the unveiling of Tesla's all-new electric aircraft. But this isn't another futuristic concept meant to stay on paper. This time, it's a tangible machine carrying a price tag so shocking that it's already disrupting the aerospace industry. Only $75,999. For context, most 4- to 6-seat electric or hybrid aircraft still cost well over $1 million. That single number instantly ignited global attention, not just for its affordability, but for what it represents: a true technological turning point that could redefine who gets to fly and how aviation itself operates in the future. Recently, the U.S. Federal Aviation Administration announced a new policy that gives greater operational freedom to small private electric aircraft. Tesla wasted no time seizing this moment. Elon Musk's company, known for transforming industries by timing innovation with regulatory windows, decided it was finally time to bring its long-rumored electric plane to reality. But this wasn't revealed through a quiet press statement. It was introduced in full spectacle as Tesla's super electric plane, a triple breakthrough in aviation engineering. Observers were told to focus on 3 major areas that separate this aircraft from anything currently in the sky. First, its propulsion system, promising an unprecedented level of efficiency for civilian flight. Second, its adaptive morphing wings able to change shape mid-air to cut drag and stretch range. And third, its radically redesigned cockpit interface. Something so futuristic that even seasoned pilots admitted it feels like a completely new era in flight control. Industry experts were quick to draw historical parallels. They compared this moment to the introduction of the jet engine in the mid-20th century, which completely transformed the world of aviation. That leap in performance back then created a new category of flight, enabling speeds and ranges previously thought impossible. Now, Tesla's backers suggest we're standing at the edge of another transformation of equal scale, one that could make short and medium-distance air travel drastically cheaper, cleaner, and quieter. If that happens, the ripple effects will reach far beyond airports and runways. Airports, once too small for traditional aircraft, might suddenly become operational hubs. Cities could expand their transportation systems vertically, connecting regions through networks of short-range, silent electric flights. Environmental concerns that have long haunted aviation could diminish dramatically. Yet not everyone is convinced. The skeptics ask, how can Tesla produce such an advanced aircraft for a fraction of the normal cost? Which of the company's bold claims are backed by proven data, and which remain ambitious promises awaiting real-world tests and FAA certification? Analysts remind us that every major revolution in aviation has taken years of testing, tense regulation, and enormous investment in infrastructure before reaching widespread acceptance. That constant tension between Tesla's bold promises and the slow-moving reality of aviation oversight is exactly what makes this announcement so captivating. At the heart of the presentation was Tesla's new propulsion system, the foundation of the aircraft's entire performance. Supporters hailed it as the biggest leap in aviation power systems since the first jet engines. Instead of relying on 1 or 2 massive turbines, Tesla's design distributes 23 small electric motors across the aircraft's wings and fuselage. Each motor weighs only about 47 pounds but delivers approximately 37 horsepower. When combined, they produce a total of 847 horsepower, a figure that, for its weight, far surpasses most piston-powered engines in general aviation. But raw power isn't the real innovation. Distribution is. This setup creates redundancy and safety. If 1 or 2 motors fail, the others can seamlessly compensate, maintaining stable flight. In traditional aircraft, losing even 1 engine can cause a serious emergency. Here, the system is designed to absorb multiple failures without catastrophic consequences. Something that's bound to appeal to both regulators and cautious buyers. Then came the feature that truly stunned engineers: electromagnetic vector thrust control. In conventional aircraft, direction and stability depend on moving control surfaces, ailerons, rudders, and elevators, which work by deflecting air and creating drag. Tesla claims its electric plane can skip that step altogether. Instead, it can directly alter the direction of thrust through electromagnetic field control in each motor. That means no moving flaps or rudders are needed for maneuvering. If this works as described, pilots could achieve near-instantaneous control response. Measured in thousandths of a second, something mechanical systems simply cannot match. This would also enable vertical transitions and zero-radius turns in flight, sparking comparisons to science fiction-style aircraft. Aviation enthusiasts immediately began speculating about how this could change everything from takeoff, its methods, to emergency landings. Tesla didn't stop there. Another headline feature was the plane's adaptive power distribution system. This advanced algorithm continuously, thousands of times per second, evaluates each motor's performance and redirects power to where it's needed most. During steep climbs, the vertical lift motors receive priority. During cruising, power automatically shifts to the horizontal propulsion units to maximize range. Tesla claims this real-time optimization can cut total energy consumption by roughly 1/3 compared to fixed systems used today. However, the boldest and most controversial claim from Tesla was a supposed 347% efficiency gain. That figure raised eyebrows even among Tesla's most loyal supporters. Engineers were quick to clarify that no system can literally generate more energy than it consumes. What Tesla seems to mean is that when you account for energy recovery, such as regenerative descent, where motors act as generators during landings, the net energy retention throughout a flight cycle looks several times better than that of traditional combustion engines. For context, internal combustion engines typically waste most of their fuel as heat, achieving efficiencies below 30%. In contrast, modern electric motors can reach around 90% efficiency from battery to propeller. By incorporating energy recovery during descent, Tesla is essentially capturing what was once lost. The company's 347% efficiency phrasing might be misleading in the strict scientific sense, but the point is clear: far less energy is wasted. Still, skeptics warn that laboratory simulations and field-certified flight data are very different things. How well regenerative braking and power recovery work in a turbulent atmosphere remains to be seen. Aviation's history is filled with visionary technologies that took decades to reach commercial reliability. After the propulsion system, Tesla turned to the next major highlight: the adaptive wings. If the distributed propulsion system is the aircraft's heart, these wings are its living skin. In traditional aircraft, wings are always a compromise. Engineers must choose a fixed shape that balances lift, drag, and stability for takeoff, cruise, and landing. Tesla claims to have eliminated that compromise with shape-shifting wings that can morph dynamically in flight. Each wing, according to Tesla's presentation, can integrate 127 electromagnetic actuators built into flexible carbon fiber segments. These actuators subtly change the wing's curvature, twist, and even its effective surface area in real time. During takeoff, the system increases the wing's bulge, boosting lift by expanding the wing's area by over 20%. If accurate, this would raise the lift coefficient to levels higher than most small aircraft on the market today. The benefits are dramatic. Takeoff speeds could drop from around 60 knots to just 47 knots. Runway requirements could shrink from nearly 2,400 feet to approximately 1,300 feet. That single advancement could open access to thousands of regional airports and smaller airfields currently unsuitable for most private aircraft, but adaptive wings offer more than just shorter takeoffs. By continuously changing shape during flight, they can minimize drag, extending range while maintaining stability. For electric aircraft, where range is limited by battery density, this is crucial. Every reduction in drag translates directly into more miles per charge. Tesla's engineers describe the system as an intelligent, aerodynamic skin, constantly analyzing airflow, angle, and pressure to reshape itself in milliseconds. Combined with Tesla's AI flight control software, it effectively creates a self-optimizing aircraft that learns from every flight. This idea that the aircraft itself can think and adapt marks a philosophical shift. Instead of designing one fixed optimal shape for all conditions, Tesla builds a learning system that adjusts dynamically. This could represent the first step toward AI-assisted aerodynamics, where flight surfaces operate more like organic muscle than mechanical parts. Skeptics, again, point out that such complexity introduces risk. Hundreds of moving actuators, all relying on perfect software coordination, must work flawlessly. A single malfunction in midair could cause dangerous aerodynamic imbalances. But Tesla argues that redundancy and real-time diagnostics make failure extremely unlikely. Each actuator is monitored independently and can be overridden or isolated if necessary. The presentation emphasized how all these systems, propulsion, wings, and energy management work as one seamless whole. The motors talk to the wings talk to the AI flight computer, and the AI monitors every parameter from power draw,